Thank you. Look, it's an absolute pleasure to have the opportunity to join you this morning. Look, I really regret that I can't be there in person on this occasion, and I'm really grateful to Stefan and the organisers for allowing me to play a small role in this MOF conference. And let's hope that, that we can actually all get together in more peaceful times for the world. So look, it's a pleasure to be able to share some of our latest work in this area. And without going too much further, it really is very important that I acknowledge the incredible group of students who have really been at the start of the project that I'm going to talk to you about today. This is a project that has been really going in our lab for the last 5 years or so now. And of course, the last 2 years of that have been particularly difficult for all of us, including a 6-month lab closure here in Sydney. So I want to pay special thanks to all of these amazing students who are to thank for the work that we're able to present today. And particularly to thank the Australian Research Council for their funding of this work as well and all of their support over the years. So let me first start by giving you a bit of a broad overview of what I'm most passionate about in the field of metal organic frameworks. We are really interested in how electron and charge migration happens within these three-dimensional assemblies. And really, I think of the metal organic framework scaffold a little bit like a playground for the coordination chemist. My talk today is really going to focus on quite fundamental properties of metal organic frameworks. But as you might understand, by understanding these fundamental charge transfer interactions, it really does underpin a whole range of potential applications, everywhere from energy storage and conversion through to using these materials for electrical swing gas separations to electrochemical sensing and electrocatalysis. The list goes on. So not only from the fundamental point of view, but also from the point of view of how we might harness these electrochemical and electroactive properties to perform useful functions and useful applications. So really, the starting point for us about a decade ago was asking the question of how could we probe electroactivity in metal organic framework materials? And at the time, we were quite well versed in methods for solution state electrochemistry, but not so well versed in techniques for really probing and interrogating solid materials like metal organic frameworks. So what we were particularly interested in was that aspect of getting real-time information about spectroscopic properties of metal organic frameworks as we looked at their various electroactive states. So let me just give you really a brief prelude, if you like, into what we like to call our toolbox of techniques for exploring the spectroscopic properties of MOFs as a function of their redox states. So I'll just really cherry pick a few examples. The earliest technique that we developed was a UV visible spectroelectrochemical technique. So here, this is what we might class as a traditional 3-electrode cell, but in this cell, we incorporate a handheld spectrometer, so we can basically image the surface of the electrode, which contains the metal organic framework as we move through the electrochemical process. So this has been really powerful and given us some really important insights into the properties of metal organic frameworks as a function of their redox state. And perhaps it's really important to explain that we took a lot of inspiration in the early days from very rich areas of chemistry, including the famous organic metals or organic charge transfer salts. And a lot of this work has been done with a wonderful colleague in China at Nanjing University, Professor Jinglin Zhao. Jinglin and I share a love of tetrathiophenylene. And the reason it's such an interesting functional component, and just take, for example, this archetypal organic metal, which is a conductive charge transfer salt. It's fully organic. And the donor tetrathiophenylene here is matched in energy by an acceptor TCNQ. So there's a very close matching of the donor acceptor energy levels. And as a result, this is quite a highly conductive material. In fact, if you compare the conductivity, which is 10 to the 4 Siemens per centimetre, with that for metallic copper, you'll note that actually it's only an order of magnitude of the conductivity of metallic copper itself. So we have taken a great amount of inspiration from these to build metal organic frameworks that incorporate some of these electroactive components like the tetrathiophorbulene. So let me give you an example of how we can apply our solid-state spectroelectrochemical methods to understand more about the spectroscopic properties of these electroactive MOFs. This is, just by way of example, a nice proof of concept where we use here a tetrathiophorbulene-based donor ligand and a naphthalene diamide-based acceptor ligand. So this is a diamondoid framework that's a donor acceptor framework. In the solid-state cyclic voltammogram, it exhibits 5 distinct electroactive or redox states, if you like, 2 due to the tetrathiophorbulene and 2 due to the naphthalene diamide. So we can reversibly access all of these states, and using our solid-state spectroelectrochemical methods, we basically start with the spectrum here in black. Interestingly, this band here in the visible is the charge transfer or donor acceptor charge transfer transition. If we reduce the framework and use a reducing potential, that charge transfer transition diminishes. But if we go back and reoxidize the framework, then we regain the charge transfer transition. So it turns out that we can reversibly cycle between, if you like, the +1 and the -1 states here. We can cycle around and round. If we try and push the potential, though, too far negative or too far positive, the entire metal organic framework actually degrades and dissolves into solution. So we've gone a step further, and the question is then, if we're actually generating radical states in the course of this redox process, could we pick those up or interrogate those using EPR? And in fact, we can do this, and we have an analogue here of the spectroelectrochemical method that uses EPR spectroscopy. So my students call this the Sushi roll method, and the idea is that we incorporate the metal organic framework into essentially a platinum gauze. It's rolled into the gauze, and we can then apply a potential, a reducing or an oxidizing potential. In this case, we start off with the black curve, which has the as synthesized MOF with the TTF radical cation and naphthalene diamide radical anion. If we apply a reducing potential, we reduce the amount of the radical cation and increase the amount of the naphthalene diamide radical anion. We can use, coupled with this, computational methods, and we can predict that there indeed is a charge transfer transition that is observed. And without going into great detail, we can also extend these solid-state spectroelectrochemical methods to Raman spectroscopy as well. So here we use a screen-printed electrode that's mounted onto a confocal Raman instrument, and we can apply, in this case, an oxidizing potential, follow how the vibrational frequencies evolve as a function of that potential, and understand at an intimate level in terms of the framework components, how the redox states of those framework components are evolving in time. So again, that was just to cherry pick a few examples of some of this toolbox of techniques. And I wanted to share with you then really this direction we've gone in now, which is not just exploiting the electroactive properties of metal organic frameworks, but actually discovering that in these electroactive frameworks, there are an additional multifunctional properties that we can harness as well. And I want to give you an example of one particular story today that has really, really been of a great amount of interest in our lab. So we've taken a great deal of inspiration from nature in the design of metal organic framework systems, and in particular, in thinking about charge transfer transitions that can occur in these electroactive metal organic frameworks, we think a lot about charge transfer transitions that are prevalent in nature. For example, the colours of gemstones like sapphire, the colours of minerals in meteorites like hibonite, for example, in this well-known Murchison meteorite, and even charge transfer processes that lie right at the heart of photosynthetic processes in nature. These are all examples of inspiration that we've taken in terms of designing our metal organic frameworks. So these charge transfer transitions can be intrinsic, or we could apply some type of external stimulus, if you like, be that light or pressure or electrochemical or chemical potential, to instigate these types of transitions. So the story really starts here, and we call these cofacial metal organic frameworks. In fact, we've been through a period of time in the lab where we almost can't stop making cofacial metal organic frameworks, but they have some really intriguing properties. So let me share with you the first example from the group, and then let me share how this has really evolved over the last 5 years. So this is a cofacial MOF where you'll note here we have these thiazole-thiazole ligands that are almost in what you'd describe as a double windowed arrangement in the MOF. Now these are within pi stacking distance, and I should mention that here we have interpenetrated frameworks, so there is very little pore space in actual fact. But the stacking distance here is within pi stacking distance, and this gives rise to a really interesting phenomenon known as through space intervalence charge transfer. So what I mean by that is, using our spectroelectrochemical methods, if we apply a reducing potential to this metal organic framework, what we find is we actually generate a new spectrum, and this is a spectrum that corresponds to a mixed valence state of the framework. So in other words, the neutral framework is reduced, and there is a charge transfer or a special type of charge transfer interaction called an intervalence charge transfer interaction between what is formerly the neutral state of the thiazole-thiazole and the radical anion state. So this is a mixed valence state. Interestingly, this band in the near infrared region is reminiscent of an intervalence charge transfer transition. And then we have peaks in the visible region, which is corroborated here by the EPR spectrum at exactly the same potential, showing that we have radical formation. And indeed, that's the radical of the thiazole-thiazole. So this has really led to a kind of a foray of different members of this family of cofacial metal organic frameworks. And one of these is quite interesting. In fact, it turns out with the mixed valence state, we can generate what we call super reductant radicals. And what I mean by that is we find that there is a really special stability of the mixed valence state. In fact, if you generate these radicals, they will sit around for a day or more, and slowly, the system will reach its, regain its neutral state. So that turns out to be quite powerful, and we've used that over the years to and harness that to do, for example, carbon dioxide electroreduction. But actually the example I wanted to tell you about today was an example that harnesses electroactivity in metal organic frameworks, but also brings about mechanical motion as well. So let me tell you a little bit about this story, and then I'll also share with you some of our very latest data out of the lab. So this is what we might like to call the parent metal organic framework. It exhibits that same double-walled or cofacial arrangement. In this case, we have a tetrathiafulvalene inspired ligand. And if you just sit this MOF out on the laboratory bench, over the course of a day, just under ambient light streaming in through the windows, it actually undergoes what we've now found to be a double 2+2 photocyclization event. And so we've been able to crystallographically characterise both the cofacial state, the totally cyclized state, and we've also captured some intermediates as well. Now, this is quite interesting. We can actually follow the photocyclization phenomenon in situ using powder X-ray diffraction and also using in situ Raman spectroscopy. And we can marry that up now with computational predictions as well that corroborate and provide good evidence for the cyclization of the tetrathiafulvalene to form this cyclobutane. What's quite interesting here is we can actually go in the reverse direction as well. So if we heat the system up, in this case at 150 degrees, we can reverse that photocyclized state and regain the cofacial state. Unfortunately, we can't do this more than a few times on single crystals because they crack apart but we can certainly cycle a powder of this material. It has some rather interesting properties. So in the cophasal and photocyclized state, in fact, there are quite distinct gas adsorption properties. And so we are now just getting at the heart of the underlying reasons for these differences in gas absorption. But in general, what we find is that for the cyclized state, you'll note that we actually have a much more profound uptake of certain gases, such as carbon dioxide, compared with the cophasal state. So there's more to come from us in terms of understanding this type of gas adsorption application. Now, interestingly, what happens when we photoradiate these crystals is they actually shrink. And so there's a mechanical motion attached to that photoradiation. And with one of our great colleagues at the Australian National University, who is able to run in situ AFM spectroscopy, we've been able to show that if you drag the tip or track the tip, an AFM tip, across a crystal of one of these photoactive metal organic frameworks, and you do this as a function of time under light irradiation, then the height of the crystal actually decreases, and the height differential here is about 11%, which is in line with what we observe for the shrinking, if you like, of the single crystal. Now, it's not just the mechanical properties, but in fact, it turns out the electrochemical and optical properties are also quite distinct between the cophasal and the cyclized state. So in the cophasal state, we observe both the redox processes forming the radical cation of the tetrathiophorbulene and the dication. In the cyclized state, if you like, we switch off that electrochemical property because we've now really changed the molecular orbital distribution of that system. So in looking into the underlying mechanism here, we looked at a couple of mechanisms, both the singlet and triplet mechanism. And the singlet mechanism, to really cut a long story short, is where we have photocyclization at just one end of the cophasal pair. In the triplet mechanism, we are looking at really a concerted mechanism where we have photocyclization at both ends. And what we tend to find here is that it's really the singlet mechanism that is preferred. And we think that in particular in the metal organic framework scaffold, you have these cophasal TTF units really locked into place, if you like. So this is quite distinct from an isolated cophasal dimer of TTFs. Within the MOF scaffold, it's all quite rigidly held, if you like. So over the last 5 years, our journey has really taken us in multiple directions. And one of my students put together this great sort of summary, if you like. I won't go through it in great detail, excepting to say I just thought I would cherry pick a couple of small examples of insights that we've gained that I was keen to share with you today. So we've made a whole library, if you like, of these MOFs, incorporating both a shorter and a longer version of the tetrathiophorbulene, along with a range of different coligands. Interestingly, these all form structures with the cophasal arrangement of the tetrathiophorbulene, but interestingly, the distances between the tetrathiophorbulene as well as the slippage, both horizontally and vertically, actually differs between the different members of the series. So if you like, we can kind of distinguish the distance between the cophasal units, as well as other structural parameters like the vertical and the horizontal slippage. So as you might expect, we also observe these intervalence charge transfer transitions in these cophasal frameworks with TTF. And interestingly, there are actually two intervalence charge transfer bands, which using computation, we've been able to track to a formally neutral to radical cation intervalence charge transfer, as well as what is really a radical cation to radical cation transition forming a dication. So we can characterize both of these transitions. And in fact, this is almost a really good example of the use of Marcus Husch classical two-state model for understanding intervalence charge transfer. And to sort of summarize the key point here, the parameter HAB is an important one that tells us something about the extent of electronic delocalization in the system. So if we know the extinction coefficient if we know the energy of the bands, if we know their bandwidth, and if we know the distance between these cofacial ligands, then we can estimate in some way what we might expect the extent of electronic delocalization to be. And in general, what we find is the longer the linker, the higher the extent of electronic delocalization. And the reason we believe for that is actually the ligands are able to get into closer proximity with one another, and the interaction, if you like, between them, the electronic interaction, is much stronger. So looking across this sort of library of MOFs that we have, what we've really been able to determine is that the longer the linker, the shorter the distance between the cofacial units, and the stronger the electronic coupling. So in short, this is really a beautiful demonstration of the Marcus-Hush distance dependence of electron transfer. As well as that, we were really intrigued by the question of how does the rate of this photocyclization vary as we change these structural parameters? How does it vary as we change the distance between the units, the horizontal and the vertical slippage? And we were also quite intrigued by the fact that really there was very little quantitative information about photocyclization in MOFs present in the literature. So using in situ photoirradiated Raman spectroscopy, what we were able to do was really follow closely the evolution of Raman signals. And here we follow a couple of key stretches at 1520 and 1560 wave numbers. And that allows us to plot really the extent of photoconversion. Now, there are a couple of models that are used in the literature to understand photocyclization. I just wanted to touch on one of them in the 1 or 2 minutes that I have remaining. This model is called the JMAC model, and it has been applied to 2+2 photocyclizations in purely organic crystals. But we were really curious about its application to metal organic frameworks, and in particular, the prospect of being able to quantify photocyclization rates. And interestingly, in this model, we're able to extract from the slope of the linearized plot what we call the Abrami constant. So this gives us some idea of what is really termed the dimensionality of photocyclization. So in other words, an Abrami constant, if you like, below 1 tells us that this is a random propagation event, and so on and so forth. It tells us something about the dimensionality, if you like, of the photocyclization. So just to offer one example here, and then I'll show you how this compares for the whole series. Here's the example of the cofacial framework with the stilbene dicarboxylate co-ligand. You'll note that actually the temperature dependence of the rate constant optimizes at a particular temperature. Here it's somewhere around 10 degrees. And I should also add that this is the culmination of many, many experiments. So the error bars here are meaningful and are very important. But the optimization here of the temperature of photocyclization, or the optimum temperature of photocyclization, is quite important. And it really does reflect the fact that the reaction rate is dependent upon the probability of those reacting bonds being within a particular zone. So beyond, or at temperatures higher than the optimum, those reacting bonds are not spending a sufficient amount of time in contact with one another to photocyclize. And at lower temperatures, likewise, it's a little bit too cool for that photocyclization event to occur in an optimum fashion. So the last picture I really want to leave you with is the start of our understanding of this broader picture of structure-function relationships in terms of the relative kinetics, if you like, of this double 2+2 photocyclization event. So as we change the co-ligand, what you'll notice is that actually the temperature at which, or the optimum temperature of photocyclization actually varies depending upon the co-ligand. And to cut a very long story short, what we find is that the larger the cofacial distance, the higher the temperature at which the reaction rate is maximized. And this makes sense because if there's a larger distance between the tetrathiophorbalenes, you can understand that actually you need more thermal energy in order for those, the vibrational motion to allow those ligands to come in contact and photocyclize. The other really interesting correlation we find is that the larger the electronic coupling, or the HAB, this correlates with a faster reaction rate. And we're trying at the moment to really understand the underlying rationale for that particular observation. So to sum up then, I hope what I've been able to show you today is that using this toolbox of techniques that we have, we've been able to really interrogate some quite fundamental properties of electroactive metal organic frameworks. As you can understand, if we can harness these fundamental properties, then of course it leads us to a whole range of potential applications. And one that we're quite interested in is the notion of using these multifunctional MOFs as optical actuators. And just finally, I've given you a snapshot of the wonderful people who have done all of this work in my group over the years, particularly under the really difficult circumstances over the last 2.5 to 3 years. And I'm absolutely indebted to them and thank them immensely for all of their hard work. And I'd like to thank again the Australian Research Council, who have supported all of this work over the last 5 years. And thank you again for being there when I'm not able to physically be there. Thank you. Back to you, Chair.
Thank you very much, Professor D'Alessandro, for this very inspiring talk. So the stage is open for some questions. We have 2 minutes, so there are maybe 2 for questions. Yes, please.
Oh, thank you. That was a really elegant and beautiful talk. A simple question from near the beginning. When you have these oxidation reduction reactions in the electrochemistry going on inside these MOFs, are there counter ion effects, or is it somehow internally compensated, or what's going on there?
Yes, that's an excellent question, and you're absolutely right that there must be charge compensation. So in concert with the electrochemical process, and really I've only talked about what we might consider as the framework-based electrochemical process, but there is a coupled ion motion. So this becomes quite complicated, and I think it's important that I say that the caveat here is that there are many more elegant ways to perform solid-state electrochemistry. For example, very elegant epitaxial growth of metal organic frameworks on electroactive substrates. Here, our method is literally using a mechanically immobilized metal organic framework on a surface. So I think it's important to say that really we are probably only accessing the electrochemical properties of very much the surface, or perhaps, you know, a few layers into the metal organic framework. This is certainly not a bulk technique. We do, in concert with all of our spectroelectrochemical work, do chemical oxidations and reductions to understand the bulk properties. And we couple that information about the bulk properties with what we learn about the dynamic characteristics, if you like, in real time of the metal organic frameworks. And really it's not one or the other. It's understanding that whole picture that helps us to understand the coupling of the, if you like, electron hopping or charge hopping through the backbone of the framework and the coupled ion motion through the pores.
Thank you so much for the comprehensive answer. And I have one last very short question maybe. When you talk about the change between the cofacial and the cyclized state, do you think that can be also used as a kind of switch for a molecular switch later on, that you can really release something because the uptake isotherms, they were changing? So could that be a kind of switch also?
Yes, actually, we've got a piece of IP around essentially doing that. So if you like, the MOF can host guest molecules, but when you shine light, it actually, because it contracts, it actually squeezes those guest molecules out of the pores. The caveat, and really what we're working on at the moment, is being able to do that in a reversible fashion. So this is not easy for single crystals. It does work for the powder, but we have a long way to go in terms of raising the material readiness, if you like, of that particular process.